There's a moment in the history of our universe so profound, so pivotal, that it changed everything, yet it happened in utter silence, in a darkness so complete it's almost impossible to fathom. Picture this, a cosmos without stars, without galaxies, just an endless sea of blackness stretching in every direction. Then, like the first note of a symphony, light burst forth, not just any light, but the echoes of creation itself, rippling through the void and leaving behind a map of its journey. This isn't science fiction. This is the story of when cosmic light echoes crashed into ancient darkness and left behind a blueprint of the universe's infancy. And today, we're going to trace those echoes, uncovering secrets that have been waiting billions of years to be heard. Think of these light echoes as cosmic breadcrumbs scattered across time and space. They're not just remnants of the past, they're active storytellers, whispering clues about how the universe grew from a formless void into the glittering expanse we see today. Scientists have spent decades piecing together this puzzle, and what they've found is nothing short of breathtaking. These echoes reveal moments of transformation when the first stars flickered to life, when galaxies began to spin into existence, and when the very fabric of reality shifted. It's as if the universe left us a treasure map, and we're only now learning how to read it. But here's what's truly mind-blowing. Every time we detect one of these cosmic echoes, it's like receiving a message from the dawn of time. The light we're capturing today began its journey when the universe was just a fraction of its current age, carrying with it the fingerprints of the earliest cosmic events. What mysteries does it hold? What stories are still waiting to be decoded? That's the adventure we're embarking on in this video, a journey through the echoes of light that shaped everything from the tiniest particles to the grandest galaxies. By the end, you'll see the night sky not just as a collection of stars, but as a living, breathing chronicle of the universe's most epic tale. So, are you ready to step into the echoes? Let's begin. To understand the birth of cosmic light, we have to rewind to a time when the universe was nothing like it is today. No stars, no galaxies, just a hot, dense soup of particles buzzing in the dark. For hundreds of thousands of years after the Big Bang, the cosmos was so thick with free electrons and protons that light couldn't travel more than a tiny distance before being scattered, trapped in a fog of matter. But then, something extraordinary happened. As the universe expanded and cooled, electrons and protons finally began to combine, forming the first atoms of hydrogen. This moment, called recombination, was like flipping a cosmic switch. Suddenly, photons, those tiny packets of light, could travel freely for the first time, no longer bouncing endlessly in the chaos. That burst of liberated light is what we now call the cosmic microwave background, the oldest glow in the universe, still detectable today as a faint whisper of radiation filling every corner of space. This was the universe's first true light, but it wasn't like the starlight we know. It was more like a dull, uniform haze, a pale echo of the Big Bang's fiery birth. Yet within that glow were tiny fluctuations, slight variations in temperature and density imperceptible at first glance, but monumental in their implications. These imperfections were the seeds of everything to come. Over billions of years, gravity would amplify those subtle ripples, pulling matter together into the first stars, the first galaxies, the first structures of the cosmos. In a way, those early photons were the universe's first cartographers, tracing the blueprint of the cosmic web long before anything visible had even formed. What's astonishing is that we can still read that map today. The cosmic microwave background isn't just a relic, it's an active guide revealing the universe's hidden architecture. By studying its patterns, scientists have uncovered clues about the shape of space, the nature of dark matter, even the universe's ultimate fate. Every time we point a telescope at this ancient light, we're not just looking back in time, we're decoding the very foundations of reality. And the story doesn't end there. Those first echoes set off a chain reaction, igniting the cosmos with starlight, shaping galaxies, and ultimately paving the way for everything we see and everything we are. After that first flash of cosmic light came a silence so deep it lasted millions of years, a period astronomers call the Dark Ages. Imagine a universe where not a single star flickered, where space itself was a vast, empty theater with no actors yet on stage. The glow from recombination had faded, leaving behind only hydrogen atoms drifting in the cold expanse. But this wasn't just stillness, it was a darkness with purpose. Those hydrogen atoms acted like cosmic sponges, soaking up any stray photons, trapping light in an endless game of catch and release. For eons, the universe remained shrouded, a place where even if you could travel through it, you'd see nothing but an unbroken veil of black. Yet within that darkness, invisible dramas were unfolding. Tiny pockets of matter, slightly denser than their surroundings, began pulling in more gas through gravity's quiet tug. The universe wasn't idle, it was preparing. Without light, without stars, these hydrogen clouds were the only architects at work, slowly sculpting the framework for everything to come. Scientists call this the cosmic dawn, but dawn suggests a sudden burst of light. In reality, it was a painstakingly slow process, like waiting for a single ember to ignite a forest. So how do we study an era with no light to observe? It's like trying to reconstruct a symphony from the silence between its notes. Researchers use ingenious indirect methods, tracking the faint ripples in the cosmic microwave background, simulating the physics of early gas clouds, even listening for the whispers of hydrogen's natural radio signals. These clues tell us the Dark Ages weren't just empty time. They were the universe's quiet workshop, where the raw materials for stars and galaxies were meticulously gathered. Then came the spark. Somewhere in one of those dense hydrogen clouds, gravity's pressure grew too intense. Atoms collided, temperatures soared, and for the first time since the Big Bang, nuclear fusion ignited. A star was born. Its light, fierce and new, pierced the surrounding darkness, stripping electrons from hydrogen atoms in a process called reionization. Slowly, star by star, the fog of hydrogen began to clear. The universe, once opaque, became transparent again. But this time, it wasn't the uniform glow of recombination. Now the cosmos flickered with countless points of light, each one a beacon in the void. This was the moment light echoes truly began. Those first stars didn't just illuminate their immediate surroundings. Their photons raced outward, bouncing off gas clouds, weaving through the cosmic web, leaving behind trails we can still detect today. The Dark Ages had ended, but their legacy was written into every echo of light that followed. The moment that first star ignited, it didn't just pierce the darkness, it rewrote the rules of the cosmos. These weren't the tame, long-lived stars we know today. They were titans, hundreds of times more massive than our sun, burning ferociously and dying young in spectacular supernova. Their ultraviolet radiation was so intense, it ripped electrons from surrounding hydrogen atoms, stripping them back into free particles in a process called reionization. Picture it like a cosmic wildfire where each new star didn't just shine. It scorched through the primordial fog, carving transparent pathways for light to travel. This was the universe's second great liberation of light, and it left echoes we're still deciphering. Detecting these ancient signals is like trying to hear a whisper across 13 billion years. The light from those first stars has been stretched by the expansion of the universe, shifted into faint radio waves that blend into the background noise of space. Scientists hunt for these whispers using arrays of radio telescopes, each one tuned to catch the faint signature of hydrogen atoms being bathed in that first starlight. It's painstaking work, like listening for a single instrument in a symphony playing at the edge of audibility. But hidden in those whispers are revelations about how the cosmos transformed from a featureless void into a structured, luminous universe. What makes these echoes so valuable is their honesty. Unlike light from later stars, which carries the fingerprints of countless interactions, these early photons are pristine messengers from a simpler time. They bear imprints of the universe's infancy, the density of matter, the push of dark energy, even the ghostly presence of cosmic filaments that would one day form the largest structures in existence. By studying them, we're not just observing history, we're reading the universe's diary written in wavelengths of light, yet the challenges are immense. Earth's atmosphere, human-made radio interference, even the glow of distant galaxies all conspire to drown out these faint signals. That's why projects like the James Webb Space Telescope and next-generation radio observatories are so vital. They are time machines, peeling back layers of cosmic noise to reveal the universe's first chapters. And what they've already shown us is astonishing. Hints of galaxies forming earlier than anyone predicted. Clues that reionization wasn't a uniform process but a patchwork of brilliant flares in the darkness. These echoes don't just tell us where we came from, they hint at where we're headed. The same forces that shaped those first stars are still at work today, weaving new structures across the cosmos. Every time we decode another fragment of this ancient light, we're adding another piece to the greatest puzzle of all, the story of everything. Light echoes are the universe's way of preserving its own history, like celestial postcards sent across time. Imagine shouting into a canyon and hearing your voice bounce back. Now stretch that idea across light years. When light from a star or cosmic explosion travels outward, it doesn't just vanish. Some of it slams into clouds of gas, dust, or even entire galaxies, scattering in new directions. These reflections, arriving millions of years later, carry priceless information: the fingerprint of their source, the composition of the space they crossed, and even clues about the forces that shaped their journey. Unlike sound echoes that fade in seconds, light echoes can persist for millennia, offering us a way to study events too distant or ancient to witness directly. Think of them as cosmic time capsules. A supernova might flash and fade in a matter of weeks, but its light echoes linger, ricocheting through interstellar space like ripples in a pond. By analyzing these delayed signals, astronomers can reconstruct the explosion's original brightness, its chemical makeup, and the environment it erupted into, all from an event that technically ended before Earth's continents had fully formed. It's as if the universe left us a trail of breadcrumbs, each one revealing a different chapter of its story. What makes these echoes so powerful is their ability to turn cosmic structures into mirrors. A single burst of light can produce multiple reflections, each one bouncing off a different nebula or dust cloud at varying distances. The result, a layered record of the same event, seen from different angles and times. It's like having a multi-camera setup for the cosmos, capturing the same moment through different lenses. And because light travels at a fixed speed, the delays between these echoes act as a cosmic stopwatch, letting scientists measure vast distances with precision. But here's the real magic. These echoes don't just show us the past, they reveal how the universe has changed. The light from an ancient quasar, for example, might pass through several galaxy clusters before reaching us. Each interaction subtly alters its properties, imprinting details about the matter it encountered. By decoding these changes, researchers can map the distribution of invisible dark matter or trace the evolution of galactic winds. Every echo is a puzzle piece, helping us assemble a dynamic, three-dimensional map of cosmic history. This is why telescopes like Hubble and James Webb don't just stare at objects, they listen for these whispers of reflected light. When they catch an echo from a long-dead star, it's not just a scientific breakthrough, it's a conversation across time. We're not merely observers of the universe's past, we're detectives, piecing together clues from light that's been traveling since before our solar system existed. And with every echo we decode, the map of our cosmic origins grows clearer. Light echoes are more than just cosmic reflections. They are a masterclass in the physics of how light interacts with the universe. To understand how they work, picture a flashlight beam hitting a wall. Some light bounces directly back, but some scatters off dust particles in the air, creating a faint glow around the central spot. Now scale that up to interstellar dimensions. When a star explodes or a quasar flares, its light doesn't travel unimpeded. Instead, it slams into vast clouds of interstellar dust and gas, which act like cosmic mirrors, redirecting some of that light in our direction. These clouds aren't solid surfaces but diffuse collections of tiny particles, each one deflecting photons like microscopic prisms. The result: light from a single event arrives at Earth multiple times, first as the direct beam, then again as delayed echoes bouncing off dust at different distances. The key to decoding these echoes lies in their journey. Interstellar dust isn't just passive scenery, it's an active participant in shaping the light story. Dust grains, often no larger than a wavelength of light, absorb some photons and scatter others, subtly altering the light's color and intensity. Gas clouds, on the other hand, can imprint their own signatures, absorbing specific wavelengths to create dark lines in the echo's spectrum, like a barcode revealing the cloud's chemical makeup. This interplay between light and matter transforms every echo into a layered record, carrying information not just about the original source but about the cosmic terrain it traversed. Detecting these faint signals is like trying to spot a candle flame from across a foggy lake. Astronomers rely on telescopes equipped with hypersensitive detectors, capable of picking up light 1 billion times dimmer than what the human eye can see. Instruments like the Hubble Space Telescope or the James Webb Space Telescope are essential, but so are ground-based observatories with specialized filters that isolate the echo's specific wavelengths from the background glow of the night sky. Sometimes the telltale sign of an echo isn't brightness at all but a subtle shift in color, light stretched to redder wavelengths by the expansion of the universe, a phenomenon called redshift. What makes light echoes truly unique is their time delay effect. Because light travels at a fixed speed, echoes from the same event can arrive centuries or even millennia apart, depending on how far the light had to detour. It's like hearing an orchestra play a note, then hearing the same note bounce back from different walls in a concert hall at different times. This delay isn't just a curiosity, it's a tool. By measuring the time between the original light and its echoes, astronomers can map the three-dimensional structure of the dust clouds themselves, turning the cosmos into a giant sonar system. To piece together these cosmic messages, scientists use tools that would make any detective proud. Spectrographs dissect the light into its component colors, revealing the fingerprints of atoms and molecules in the echoing dust. Polarimeters measure how the light's orientation has changed, hinting at the shape and alignment of the particles it encountered. And advanced computer models simulate the echo's journey, testing theories about the density and composition of interstellar space. Together, these tools transform faint glimmers into profound insights, letting us read the universe's history written in light. But the real magic happens when we combine these techniques. A single echo might tell us about a supernova's explosion, but a series of echoes can reveal how that explosion shaped its surroundings over centuries. They show us how energy ripples through galaxies, how dust clouds evolve, and even how the universe's expansion accelerates over time. Every echo is a snapshot of cosmic processes frozen in light, waiting for us to develop the tools to unlock them. And as our technology improves, so does our ability to listen to these whispers from the past, each one a clue in the grand mystery of how the universe grew from darkness into light. Mapping the cosmos with light echoes is like turning the universe into a giant time machine, one where every reflection holds coordinates to a different epoch. These echoes don't just tell us what happened, they show us where and when, creating a three-dimensional atlas of cosmic history. Imagine tracing the path of a photon that left a dying star 13 billion years ago. As it zigzags through space, bouncing off interstellar clouds, each detour etches a new layer into its journey. By measuring the delays between these echoes, astronomers can triangulate the positions of invisible dust clouds and galactic structures, effectively mapping the universe's hidden scaffolding. What makes this technique so revolutionary is its ability to reveal the distribution of matter, both seen and unseen. When light echoes bend around galaxy clusters or slow slightly as they pass through dense gas, they betray the presence of dark matter, the elusive substance that makes up most of the universe's mass. It's like watching ripples on a pond distort around submerged rocks. You might not see the rocks directly, but the way the water moves gives them away. These subtle deflections allow scientists to chart cosmic geography on scales impossible to observe with traditional telescopes, exposing the vast, web-like filaments of matter that connect galaxies across billions of light years. But light echoes do more than map space, they also encode the universe's expansion. As space stretches, it elongates the wavelengths of traveling light, shifting echoes toward the red end of the spectrum. By comparing the redshift of direct light from an event to its delayed echoes, researchers can measure how much the cosmos has expanded during the time between those arrivals. It's a cosmic measuring tape, revealing the rate of the universe's growth with unprecedented precision. This approach has birthed an entirely new field, cosmic archaeology. Just as geologists study rock layers to reconstruct Earth's past, astronomers now sift through layers of light echoes to excavate ancient celestial events. A single echo might preserve the chemical signature of a supernova's explosion, while another reveals the temperature of intergalactic gas from an era before our solar system existed. These echoes aren't just reflections, they're fossils of light, preserving moments the universe has long since moved past. Groundbreaking discoveries have already emerged from this technique. Light echoes confirmed the existence of dark energy, the mysterious force accelerating the universe's expansion, by revealing how ancient supernovae appeared dimmer than their redshift suggested. They've exposed missing baryonic matter, ordinary atoms that had vanished from telescopic surveys, hiding in diffuse clouds between galaxies. And they've even allowed astronomers to reconstruct the explosive deaths of stars that flared and faded before Earth's continents had fully formed. One of the most stunning examples came from the light echoes of a supernova observed in the Large Magellanic Cloud in 1987. While the initial explosion faded within months, its echoes continued bouncing off distant dust clouds for decades, offering a slow-motion replay of the event. By analyzing these delayed signals, scientists decoded the supernova's geometry, its chemical fallout, and even the turbulent motions of debris invisible in the original blast. It was like rewinding a cosmic film strip, frame by frame. Now, with next-generation telescopes honing their sensitivity to these whispers from the past, we're poised to uncover even deeper secrets. Light echoes from the universe's first quasars could reveal how black holes grew to monstrous sizes so quickly after the Big Bang. Faint reflections from primordial gas clouds might expose the mechanisms that sparked the earliest stars. Each echo is a thread in the tapestry of cosmic history, and as we learn to follow them, we're not just mapping the universe, we're reading its autobiography, written in the language of light. When a star reaches the end of its life in a supernova explosion, it doesn't just vanish. It sends out a shockwave of light so powerful it can illuminate the cosmos for centuries. But here's the twist: long after the initial flash fades, that light keeps traveling, bouncing off interstellar dust clouds like a cosmic pinball. These reflections, called light echoes, create eerie glowing rings around the site of the explosion, expanding outward like ripples in a pond. What makes them so valuable isn't just their beauty, it's the way they freeze moments of stellar death in time, giving astronomers a rare chance to study supernova long after they've faded from view. Take Tycho's supernova, a star that exploded in 1572 and was observed by the astronomer Tycho Brahe. While the original event lasted just weeks, its light echoes are still visible today, 450 years later. By analyzing these delayed signals, scientists have reconstructed the explosion's geometry, measured the speed of its debris, and even identified the types of atoms forged in its fiery collapse. It's like rewinding a cosmic film reel. Each echo captures a different frame of the supernova's destruction. But these echoes aren't just celestial nostalgia, they're precision tools for measuring the universe. Because light travels at a constant speed, the time delay between the original supernova and its echoes reveals the exact distance to the dust clouds they've bounced off. It's nature's own rangefinder, letting astronomers map interstellar space with extraordinary accuracy. Even more astonishing, by comparing echoes from different angles, researchers can piece together three-dimensional views of the explosion, uncovering details about how stars die that would otherwise be lost to time. The echoes from supernova also carry chemical fingerprints. As light passes through debris clouds, certain wavelengths get absorbed by specific elements, leaving dark lines in the echo's spectrum. It's like reading a barcode of the universe's composition. Each line reveals another ingredient in the cosmic recipe. This has led to groundbreaking discoveries, like confirming that supernovae are the universe's primary factories for heavy elements, from the iron in our blood to the gold in our jewelry. Yet supernova aren't the only cosmic events that leave echoes. Quasars, the blazing cores of distant galaxies, produce their own luminous reflections when their intense radiation hits surrounding gas. Even gamma-ray bursts, the most energetic explosion since the Big Bang, create faint afterglows that linger like cosmic campfires. Each type of echo tells a different part of the universe's story, whether it's the violent birth of a black hole or the slow dance of dust clouds shaping new stars. What ties them all together is their role as time travelers. When we catch an echo from a long-dead star, we're not just observing the past, we're interacting with it, using light as both messenger and microscope. And as telescopes grow more sensitive, these echoes will reveal even deeper secrets about the nature of dark matter, the acceleration of the universe's expansion, and perhaps even the echoes of events we haven't yet imagined. Every ring of light is a doorway, and we're just beginning to step through. Quasars are the universe's ultimate lighthouses, beacons so bright they outshine entire galaxies, yet they're powered by something almost unimaginably small: supermassive black holes. These cosmic monsters, lurking at the hearts of ancient galaxies, don't just swallow light, they create it. As matter spirals toward the black hole at nearly the speed of light, friction heats it to millions of degrees, transforming it into a swirling disk of incandescent plasma. The energy released outshines every star in its host galaxy combined, blasting radiation across the cosmos. But here's the twist: that light doesn't just travel straight to us. Some of it ricochets off clouds of gas and dust, creating echoes that carry secrets about the quasar's past and the universe's youth. These echoes are more than just reflections, they're time capsules. When a quasar's light bounces off a distant nebula, it preserves a snapshot of the quasar's activity from thousands or even millions of years earlier. It's like finding a series of old photographs, each one showing the quasar at a different stage of its life. By comparing these delayed signals to the quasar's current light, astronomers can track changes in its brightness, its energy output, even the motions of matter around the black hole. One of the most startling discoveries: some quasars flicker dramatically over cosmic timescales, flaring up and fading like cosmic campfires. Their echoes reveal that these aren't steady beacons but turbulent, unpredictable powerhouses, likely as their black holes feast on intermittent bursts of gas and stars. But quasars do more than just light up their surroundings, they sculpt them. Their intense radiation ionizes nearby gas, stripping electrons from atoms and pushing material outward in colossal winds. When this light echoes off those same gas clouds, it carries imprints of their composition, temperature, and motion. Think of it like shining a flashlight through fog. The way the light scatters tells you about the fog's density and movement. Quasar echoes have exposed vast reservoirs of pristine hydrogen, left over from the Big Bang, as well as heavy elements forged in earlier generations of stars. They've even revealed galaxies in the process of being torn apart by quasar-driven winds, their gas flung into intergalactic space like leaves in a hurricane. Perhaps the most profound revelation from quasar echoes is how they trace the growth of supermassive black holes. By studying delays between a quasar's direct light and its echoes, astronomers have measured the size of the feeding zone around these black holes, the region where matter swirls before vanishing past the event horizon. These measurements show that the largest black holes in the early universe grew astonishingly fast, packing on mass equivalent to thousands of suns per year. How echoes suggest they gorged on dense gas flows during cosmic collisions, or perhaps devoured entire stars in tidal disruption events. Without these light echoes, we'd have no way to reconstruct such violent, ancient feeding frenzies. Recent observations have added even more layers to the mystery. The James Webb Space Telescope has detected quasar echoes from just 700 million years after the Big Bang, so early that theorists are scrambling to explain how black holes grew so massive so quickly. Some echoes show bizarre spectral lines, hinting at unknown physical processes near the event horizon. Others reveal that quasars weren't solitary monsters but often lived in pairs, their black holes dancing toward catastrophic mergers. Each discovery peels back another layer of the quasar enigma, showing they're not just relics of the past but active players in shaping the cosmos. What ties all this together is the way light echoes turn quasars into cosmic laboratories. They let us study black hole physics across billions of years, observe the chemical enrichment of the early universe, and even test Einstein's theories under extreme gravity. But beyond pure science, these echoes remind us that light isn't just something we see. It's a messenger carrying stories from the dawn of time. Every quasar echo is a piece of a grand puzzle, and as we fit them together, we're not just mapping the universe's history, we're uncovering the forces that made our existence possible. The cosmic microwave background is the oldest photograph ever taken, a baby picture of the universe when it was just 380,000 years old. Imagine stretching a single moment across 13.8 billion years. its light growing fainter and colder with every passing epoch until all that remains is a whisper of microwave radiation permeating every cubic inch of space. This afterglow isn't just a relic, it's our most direct window into the universe's fiery birth. When the first atoms formed during recombination, they released photons that have been traveling ever since, their wavelengths stretched by cosmic expansion from visible light into microwaves. What we detect today is that primordial glow, cooled to just 2.7 degrees above absolute zero, carrying encoded details about the universe's infancy. Hidden within this uniform haze are tiny fluctuations, temperature variations no larger than 1 part in 100,000. These imperfections are the universe's first brushstrokes, the gravitational seeds from which all cosmic structure would grow. Slightly denser regions pulled in more matter through gravity, eventually collapsing into galaxies and galaxy clusters, while less dense areas became the vast voids between them. The cosmic microwave background is more than a snapshot. It's the universe's blueprint, showing us where everything began and how those beginnings shaped the cosmos we inhabit today. The discovery of this background radiation in 1965 was one of science's greatest triumphs. When Arno Penzias and Robert Wilson first detected this persistent microwave static with their Holmdel-Horn antenna, they initially dismissed it as pigeon droppings interfering with their equipment. But after meticulous cleaning and testing, the signal remained a constant hum coming equally from all directions. It matched precisely what theorists had predicted, the cooled remnant of the Big Bang's initial fireball. This was the smoking gun, evidence that transformed cosmology from speculation into rigorous science, proving our universe had a definite beginning. Modern technology has turned this faint whisper into a treasure trove of cosmic secrets. Space-based observatories like COBE, WMAP, and Planck have mapped the cosmic microwave background with astonishing precision, revealing not just temperature variations but also the polarization of these ancient photons, a subtle twisting of light that tells us about the universe's first tremors. These patterns confirm the existence of dark matter, hint at the nature of dark energy, and even provide clues about what happened during the universe's first trillionth of a second. What makes these measurements so extraordinary is their precision. We're detecting temperature differences equivalent to millionths of a degree across the entire sky, like measuring the heat from a candle on the moon. To achieve this, instruments must be cooled to near absolute zero and placed beyond Earth's interfering atmosphere. The Planck spacecraft, for example, orbited at a special gravitational balance point called L2. Its detectors chilled to just 0.1 degrees above absolute zero. From this vantage, it mapped the cosmic microwave background with such detail that we can see the gravitational imprints of galaxy clusters that wouldn't form for billions of years after the light began its journey. Perhaps most astonishing is how this ancient light continues to reshape our understanding of reality. The cosmic microwave background revealed that ordinary matter, the atoms making up stars, planets, and us, comprises just 5% of the universe's content. It showed that space is geometrically flat to within 1% accuracy, confirming predictions from cosmic inflation theory. And its polarization patterns may yet reveal gravitational waves from the Big Bang itself, direct evidence of the universe's explosive birth. Every new analysis peels back another layer, showing that this primordial echo isn't just a static image but an active conversation, one we're only beginning to decode. As technology advances, so does our ability to listen. Next-generation telescopes aim to measure the cosmic microwave background's polarization with even greater sensitivity, potentially uncovering signatures from the universe's first moments. Others plan to study its spectral distortions, tiny deviations from perfect thermal radiation, that could reveal energy injections from the first stars or even exotic physics beyond our current models. What began as an annoying microwave hiss has become astronomy's Rosetta Stone, translating the universe's earliest chapters into a language we can understand. And with every improvement in our instruments, we're not just looking further back in time, we're rewriting the story of how everything came to be. Capturing these whispers from the cosmos requires instruments of extraordinary sensitivity, machines that can detect light 1 billion times fainter than what the human eye can see. Space telescopes like Hubble and James Webb are at the forefront of this hunt, their mirrors polished to perfection, orbiting above Earth's distorting atmosphere. Hubble's keen eye has traced light echoes from supernova in our galactic neighborhood, while James Webb's infrared vision peers even further, picking up echoes from the universe's first stars, photons stretched by cosmic expansion into wavelengths invisible to other telescopes. But it's not just about magnification. These observatories act as time machines, isolating specific layers of light that left their sources millions or billions of years ago. On the ground, radio telescope arrays like ALMA in Chile's Atacama Desert play an equally vital role. Their dishes, spread across miles of high-altitude terrain, work in unison to catch the faint radio whispers of hydrogen atoms stirred by ancient starlight. Unlike optical telescopes, these antennas detect wavelengths that pierce through cosmic dust, revealing echoes from epochs when the universe was still cloaked in darkness. And then there's the upcoming Vera C. Rubin Observatory with its 3.2 gigapixel camera designed to scan the entire visible sky every few nights. By spotting fleeting changes in brightness, the hallmark of emerging light echoes, it promises to uncover thousands of these cosmic reflections that earlier surveys missed. The real magic happens when these telescopes team up with spectrographs, instruments that split light into its constituent colors like a cosmic prism. Every element leaves a unique fingerprint in these spectra: iron, oxygen, even molecules like carbon monoxide, allowing astronomers to reconstruct the chemical makeup of echoing dust clouds. But spectroscopy does more than identify ingredients, it tracks motion. When light bounces off gas moving toward or away from us, its wavelength shifts slightly, an effect called the Doppler shift. By measuring these subtle changes, researchers can map how debris from a supernova expands or how quasar winds push through galactic gas, all from echoes that arrive centuries after the original event. Separating these faint signals from the universe's background noise is like trying to hear a pin drop in a thunderstorm. Cosmic microwave radiation, starlight from billions of galaxies, even interference from Earth's own radio chatter all conspire to drown out echoes. To overcome this, astronomers use techniques honed by decades of innovation. Adaptive optics systems on ground-based telescopes counteract atmospheric blurring in real time, while space telescopes employ ultra-sensitive detectors cooled to near absolute zero to minimize electronic noise. Advanced algorithms then sift through the data, identifying patterns that betray an echo's presence, perhaps a slight brightening in a specific wavelength or a ring of light expanding at the speed of light itself. These technological triumphs have reshaped our cosmic perspective in ways early astronomers could never have imagined. Where once we saw static points of light, we now recognize a dynamic universe alive with reflections, each one a chapter in an epic still being written. The echoes captured by Hubble have rewritten textbooks on stellar death, while James Webb's early observations suggest galaxies formed earlier and faster than models predicted. Ground-based radio telescopes have exposed vast reservoirs of primordial gas untouched since the Big Bang, and upcoming missions like the European Space Agency's Ariel will take spectroscopy further, analyzing echoes from exoplanet atmospheres for signs of alien chemistry. What unites these tools is their ability to transform light from a passive signal into an active probe, one that interrogates the universe about its past, present, and future. Every photon carries information, and every echo is a conversation across time. As our instruments grow ever more sophisticated, they're not just collecting data, they're teaching us to listen to the universe's oldest stories, written in the language of scattered light. Light echoes aren't just relics of cosmic history, they're measuring tapes stretching across the universe, revealing how space itself has grown over billions of years. One of their most profound contributions comes from redshift, the phenomenon where light stretches to longer wavelengths as the universe expands. Imagine a photon emitted by a dying star billions of years ago, carrying a specific signature in its light. By the time that photon reaches us after bouncing off an interstellar cloud, its wavelength has stretched, shifting its color toward the red end of the spectrum. This shift isn't just a curiosity, it's a direct measurement of how much the universe has expanded during the photon's journey. The longer the delay between the original light and its echo, the more dramatic the redshift, giving astronomers a way to clock cosmic growth across vast stretches of time. What makes these echoes particularly valuable is their ability to cross-check other methods of measuring expansion. For decades, scientists have relied on supernova as standard candles, objects of known brightness whose apparent dimming reveals their distance. But light echoes add another layer of precision. When a supernova's echo arrives centuries later, its redshift can be compared to the original event's redshift, effectively creating a cosmic yardstick that spans epochs. This technique helped confirm one of the most startling discoveries in modern cosmology. The universe isn't just expanding, it's accelerating. Distant supernova appeared fainter than their redshift suggested, as if something were pushing space apart faster over time. That something earned the name dark energy, a mysterious force making up 68% of the universe's energy budget, yet whose nature remains utterly unknown. Here's where light echoes become indispensable. Unlike direct observations of supernova, which capture a single moment in an object's life, echoes provide multiple snapshots of the same event across time. By analyzing how the redshift of these echoes changes with distance, astronomers can map the expansion rate's evolution with unprecedented granularity. One groundbreaking study used echoes from supernova 1987 to refine measurements of the Hubble constant, the rate at which the universe expands, revealing tensions between different methods that still puzzle cosmologists today. Another project tracked quasar echoes across billions of light years, finding subtle variations in expansion that hint at dark energy's possible fluctuations over cosmic time. Yet for all their precision, light echoes have deepened the mystery of dark energy as much as they've clarified it. Some echoes suggest the expansion rate varies slightly in different directions, challenging the long-held assumption that the universe grows uniformly. Others hint that dark energy might not be a constant force, as Einstein once proposed, but something that evolves or interacts with matter in ways we don't yet understand. The most tantalizing clues come from echoes dating back to the universe's first few billion years, which imply dark energy's influence has changed over time, a possibility that could upend our current models of cosmic evolution. The unanswered questions are as vast as the echoes themselves. Why does the expansion rate measured with nearby light echoes disagree with predictions based on the cosmic microwave background? Could unknown physics in the early universe explain these discrepancies, or is there a flaw in our understanding of gravity itself? Each new echo study narrows the possibilities while opening fresh avenues of inquiry. What's certain is that these delayed photons are more than cosmic afterimages. They're active participants in unraveling the universe's greatest enigma. As telescopes grow more sensitive and techniques more refined, light echoes may finally illuminate the dark energy riddle, revealing whether it's a property of space itself, a new fundamental force, or something even more extraordinary. Until then, every echo is a whisper from the cosmos, urging us to listen closer. Dark matter is the universe's greatest vanishing act, an invisible substance that outweighs normal matter 5 to 1, yet refuses to interact with light in any way we can directly detect. But light echoes might finally give us a way to see the unseeable. Here's how it works. When light from a distant supernova or quasar travels toward us, its path isn't perfectly straight. Massive objects, even invisible ones like dark matter, warp the fabric of space-time, bending light like a lens distorting an image. When that bent light later echoes off interstellar dust, the reflection carries subtle fingerprints of its detour. By analyzing these distortions, astronomers can trace dark matter's ghostly presence as surely as tracking footprints in fresh snow. The genius of this technique lies in its indirect approach. Since dark matter doesn't emit, absorb, or reflect light, traditional telescopes can't spot it, but gravity doesn't lie. When light echoes curve around unseen mass concentrations, they reveal dark matter's hidden architecture, filaments bridging galaxies, halos enveloping clusters, even vast sheets stretching across cosmic voids. One groundbreaking study used echoes from a supernova in the Large Magellanic Cloud to map dark matter distributions in our galactic neighborhood with unprecedented precision. The data showed clumps of invisible mass where no stars or gas clouds existed, confirming theories that dark matter forms an intricate web binding the universe together. Ongoing projects are pushing this method even further. The Vera-C, Rubin Observatory's decade-long sky survey will track millions of light echoes, compiling the largest ever dark matter sensors through their gravitational deflections. Meanwhile, the James Webb Space Telescope is studying ancient quasar echoes to probe dark matter's behavior in the early universe, a critical test for theories about whether dark matter particles might interact weakly with each other or slowly decay over time. Already, these observations have uncovered puzzling anomalies. Some echoes bend more sharply than expected, hinting at dense dark matter clumps that challenge standard cosmological models. Could these be primordial black holes, exotic particles? The echoes aren't telling yet, but dark matter isn't the only enigma light echoes are unraveling. The same techniques are exposing cosmic mirages called rogue planets, worlds drifting freely between stars, too dim to spot directly. When one crosses a light echo's path, its gravity briefly magnifies the reflection like a lens, betraying its presence. Other researchers are studying echo distortions to hunt for intermediate mass black holes, the elusive missing link between stellar remnants and supermassive giants. Even the expansion rate of the universe, the source of heated debate among cosmologists, is being cross-checked through echo-based measurements independent of traditional methods. What makes these investigations so revolutionary is their versatility. Unlike single-mission telescopes or one-off experiments, light echoes offer a renewable resource. The same cosmic event can produce echoes for centuries, each reflection probing different regions of space, different epochs in time. As our tools grow sharper, we're not just solving old mysteries, we're discovering questions we never thought to ask. And with every echo decoded, the universe grows stranger, richer, and more wondrous than we'd imagined. Light echoes do more than just capture moments in time. They illuminate the hidden skeleton of the cosmos, tracing the vast filaments, voids, and clusters that define the universe's large-scale structure. Picture the cosmos not as a random scattering of galaxies, but as an intricate web, with dense threads of matter weaving through enormous empty spaces. When light from distant quasars or supernova travels across billions of light years, it doesn't move through empty space. Instead, it navigates this cosmic labyrinth, bouncing off gas clouds nestled within filaments or skirting the edges of vast voids. Each interaction leaves a mark on the light, subtly altering its path, its color, even its intensity. By studying these changes, astronomers can reconstruct the universe's scaffolding in astonishing detail, turning echoes into three-dimensional maps of the unseen. One of the most striking discoveries from these maps is the sheer scale of cosmic voids, regions so empty they stretch hundreds of millions of light years across, bordered by walls of galaxies. Light echoes passing through these voids arrive slightly dimmer, their wavelengths stretched further by the lack of intervening matter. In contrast, filaments, the dense highways of gas and dark matter connecting galaxy clusters, scatter light in distinctive patterns, creating echoes that appear brighter or more distorted depending on the filament's orientation and density. It's like listening to an echo in a canyon and realizing the shape of the walls from the way the sound returns. These patterns aren't just curiosities, they're critical to understanding how the universe evolved. The cosmic web structure reflects the earliest fluctuations in matter after the Big Bang, amplified over billions of years by gravity. Light echoes allow scientists to test simulations of this growth, comparing predicted filament densities or void sizes with real-world observations. For example, echoes from quasars in the Sloan Digital Sky Survey revealed a filament spanning over 500 million light-years, a thread of the cosmic web so vast it challenges theories about how quickly such structures could form. Other echoes have exposed missing baryons, ordinary matter that should exist but couldn't be accounted for, hiding in diffuse gas clouds along these filaments. But the revelations don't stop there. Light echoes have also uncovered dark galaxies, faint collections of stars and gas nearly invisible to conventional telescopes. When light from a distant quasar echoes off one of these shadowy structures, it betrays their presence through subtle spectral fingerprints. Some of these galaxies have almost no dark matter, upending assumptions about how all galaxies must form. Others appear to be fossils from the universe's first billion years, preserved by their isolation in the cosmic web. As we zoom in from the universe's vast scaffolding to individual galaxies, light echoes take on a new role, timekeepers of galactic evolution. The same echoes that map filaments can also trace how galaxies grow by cannibalizing smaller neighbors, or how their supermassive black holes flare to life. In the next segment, we'll explore how these echoes reveal the life cycles of galaxies, from their fiery births to their quiet deaths. But for now, remember this: every echo is a thread in the cosmic web, and we're just beginning to follow where they lead. Galaxies aren't just collections of stars, they're echo chambers, reverberating with light from their most dramatic moments. At their hearts, supermassive black holes power active galactic nuclei, cosmic engines so bright they can outshine every star in their galaxy combined. When these monsters feed, swallowing gas and stars, they blast out radiation that lights up surrounding dust clouds like a flashlight in a fog. Some of that light reaches us directly, but much of it takes detours, bouncing off interstellar material and arriving centuries later as luminous echoes. These delayed signals reveal how galactic cores flicker over time, showing outbursts that would otherwise fade into obscurity. Observations of nearby galaxies like M87 have captured multiple echoes from a single flare, proving these black holes don't feed steadily but in violent, sporadic bursts, cosmic feasts followed by long fasts. Beyond their brilliant cores, galaxies host sprawling star-forming regions where newborn stars illuminate their stellar nurseries. The Orion Nebula in our own Milky Way demonstrates this beautifully. Its young, massive stars flood nearby gas clouds with ultraviolet light, making them glow. But hidden in that glow are faint echoes, light that first left those stars decades or centuries ago and is now reflecting off more distant dust. By comparing direct starlight to these delayed reflections, astronomers reconstruct how star formation propagates through molecular clouds, like watching ripples spread across a pond. In distant galaxies, these echoes become time machines. The light from a star-bursting region might take 100,000 years to cross its host galaxy, bouncing off dust along the way. When we catch those reflections, we're seeing snapshots of star formation at different epochs within the same galaxy, a chronological collage of its evolutionary history. Galactic mergers add another layer to this echo symphony. When two galaxies collide, their gravitational dance flings stars and gas into chaotic new orbits, triggering waves of star formation. Light echoes preserve these violent chapters long after the galaxies have settled into one. The antennae galaxies, locked in a slow-motion collision, show brilliant echo rings marking where clusters of massive stars ignited during the merger's peak. These reflections act like cosmic timestamps, allowing astronomers to reconstruct the sequence of star formation bursts across the merging pair. Even more remarkably, echoes can betray past mergers we'd otherwise miss. The Milky Way's faint, outer halo contains ghostly reflections from ancient globular clusters, relics of smaller galaxies torn apart and absorbed billions of years ago, their last light still bouncing through our galactic neighborhood. Our own galaxy holds surprising echo riches. Near the Milky Way center, the Sagittarius B2 molecular cloud acts like a giant mirror, reflecting X-rays from a supermassive black hole outburst that occurred around 300 years ago. Farther out, the North Polar spur, a vast arc of radio emission, may be the fading echo of a titanic explosion in the galactic core millions of years past. Even local star-forming regions like Rho Ophiuchi preserve light echoes from supernova that illuminated our cosmic backyard long before humans walked the Earth. These aren't just astronomical curiosities, they're vital clues to understanding our galaxy's turbulent past and predicting its future evolution. The most fleeting echoes come from transient cosmic events, supernova, gamma-ray bursts, even stars torn apart by black holes. These cataclysms flash brilliantly, then fade, but their light continues traveling outward, illuminating new regions of space long after the original fire has died. Recent surveys have caught echoes from supernova in distant galaxies that were never seen to explode, their existence revealed only by these delayed reflections. Others have spotted light echoes without sources, mysterious rings of light expanding through interstellar space with no obvious origin, perhaps the final signals from stars that vanished before our telescopes could find them. Each one adds another stitch to the tapestry of galactic history, proving that even the briefest cosmic events leave lasting imprints on the universe. What emerges from these studies is a revelation. Galaxies don't simply exist, they communicate across time with their own light. Every echo is a conversation between past and present, a reminder that what we see tonight in the Andromeda Galaxy includes light emitted 2.5 million years ago, reflected off dust clouds that may no longer exist in their original form. As our ability to detect these faint signals improves, we're not just observing galaxies, we're learning to read their diaries, written in photons that have crisscrossed the cosmos for eons. And with each echo decoded, the story grows richer, more complex, and more astonishing than we'd ever imagined. Gamma-ray bursts are the universe's most violent flashes, cosmic detonations so powerful they outshine entire galaxies for mere seconds. But long after their initial blaze fades, something remarkable lingers. these fleeting explosions leave behind ghostly imprints as their light ricochets through space and time, bouncing off interstellar dust clouds like a celestial strobe light. The echoes from these events are more than just afterglows, they're forensic evidence, allowing astronomers to reconstruct cataclysms that would otherwise vanish without a trace. Take the gamma-ray burst detected in 2019, catalogued as GRB 1912A. For 30 seconds, it released more energy than our Sun will emit in its entire 10 billion-year lifetime. Then it disappeared from view, or so it seemed. Over the following months, telescopes caught multiple delayed reflections of that initial flash, each echo revealing a new layer of the explosion's aftermath. By analyzing how these echoes arrived at different times and angles, scientists pieced together the three-dimensional structure of the surrounding dust clouds, mapping terrain light years away with precision no direct observation could match. What makes these echoes so valuable is their ability to freeze moments of cosmic violence. A gamma-ray burst's initial light shows us the explosion itself, but its echoes capture the environment it erupted into, the density of nearby gas, the distribution of cosmic dust, even the magnetic fields twisting through interstellar space. Some echoes even carry spectral fingerprints of heavy elements forged in the explosion, like cosmic smoke signals revealing the chemistry of stellar catastrophes. These delayed signals have exposed bursts occurring in bizarre environments, some shrouded in thick cocoons of gas, others in nearly empty voids where no stars should exist. Recent studies have uncovered even stranger behavior. The afterglow of GRB 2022-07 showed echoes that brightened unexpectedly months after the initial detection, suggesting its shockwave had slammed into previously unknown dust structures. Another burst's echoes revealed concentric rings expanding at different speeds, evidence that the explosion wasn't spherical but jet-like, punching through space in focused beams. These findings are rewriting our understanding of how massive stars die, not with uniform explosions, but with asymmetric convulsions that sculpt their surroundings in complex ways. The connection to extraterrestrial life might seem distant, but light echoes provide crucial clues. Gamma-ray bursts sterilize entire galaxies with their radiation, and their echoes help us map where and how often these catastrophic events occur. By studying reflection patterns from ancient bursts, astronomers have calculated that Earth likely endured several nearby gamma-ray bursts in its history, events that may have triggered mass extinctions. Yet these same echoes also highlight life-friendly zones, regions where dust clouds are thick enough to shield planets from burst radiation, but not so dense as to prevent starlight from nurturing life. Some researchers speculate that advanced civilizations might even use light echoes deliberately. A sufficiently powerful laser aimed at surrounding nebulas could create artificial echoes, a cosmic signaling system visible across interstellar distances. While purely theoretical, this idea illustrates how fundamental light echoes are to cosmic communication. Whether natural or artificial, these reflections transform brief flashes into lasting messages, proving that even the most transient events can leave enduring marks on the universe. Light echoes might hold the key to answering one of humanity's oldest questions. Are we alone in the universe? Imagine a distant exoplanet orbiting a star, its atmosphere rich with oxygen, methane, or even industrial pollutants, potential signs of life. When starlight passes through that planet's air, certain wavelengths get absorbed, leaving behind a chemical fingerprint in the light. Now picture that light traveling for years, bouncing off a nearby dust cloud and finally reaching us. That faint echo could carry the first definitive evidence of life beyond Earth, preserved like a cosmic Polaroid. The beauty of this approach lies in its indirect power. Directly observing exoplanet atmospheres is like trying to study a firefly perched on a lighthouse. The parent star's glare drowns out the tiny world. But light echoes sidestep this problem. By analyzing reflections from interstellar dust or debris disks, astronomers effectively turn these clouds into giant mirrors, capturing starlight that has interacted with a planet's atmosphere without the blinding interference of the star itself. It's the difference between staring into the sun and examining sunlight filtered through a stained glass window. Already, researchers have detected tentative echoes from systems like TRAPPIST-1, where multiple Earth-sized planets orbit in the habitable zone, though teasing out atmospheric details remains a monumental challenge. The hurdles are staggering. These echoes are unimaginably faint, often drowned out by the glow of zodiacal dust in our own solar system or the ambient light from billions of distant galaxies. Distinguishing a biosignature like the paired presence of oxygen and methane, which shouldn't coexist without biological activity, requires precision beyond current instruments. Even the shape of the dust cloud matters. An uneven surface can scatter light in ways that mimic false atmospheric signals. It's like trying to reconstruct a symphony from the vibrations of a single violin string in a hurricane. Yet the scientific community isn't waiting. Projects like the Habitable Worlds Observatory, slated for the 2030s, aim to combine the light-gathering power of a space telescope with next-generation coronagraphs to block starlight and isolate exoplanet reflections. Others propose using the solar system's own dust clouds as natural telescopes, leveraging their light-bending properties to magnify distant echoes. Meanwhile, teams are refining machine learning tools to sift through decades of archival data, hunting for overlooked echoes that might have recorded planetary atmospheres in transit. The implications go beyond science. If we one day detect an echo carrying the signature of photosynthesis or artificial compounds, it would fundamentally alter our place in the cosmos. Philosophers have long debated whether life is a cosmic fluke or an inevitable outcome of universal laws. Light echoes could offer empirical evidence, revealing whether biospheres are rare jewels or scattered abundantly across the galaxy. And if those echoes whisper of intelligence, of technologies altering their homeworlds, the echo itself becomes a message, a signal that civilizations can leave marks on the universe long after their original light has faded. Perhaps most humbling is the timescale involved. The light we're catching today from distant exoplanets began its journey before human civilization existed. Any biosignatures we find would be snapshots of worlds as they were centuries or millennia ago, leaving us to wonder, if life flourished then, does it still? The echoes don't answer, they only remind us that the universe operates on timelines beyond human reckoning, and that our search for neighbors is also a search for our own cosmic context. Light echoes do more than expand our scientific understanding. They stretch the boundaries of human thought, forcing us to confront profound questions about time, existence, and our minuscule yet meaningful place in the cosmos. When we observe photons that have traveled for billions of years, we're not just collecting data, we're engaging in a form of time travel that blurs the line between past and present. The astronomer Carl Sagan once described these echoes as messages from the universe's childhood, reminding us that every glance at the night sky is a glimpse into a living museum where the light from long-dead stars still whispers its story. This realization unsettles our everyday perception of time as linear and absolute, replacing it with a fluid, interconnected tapestry where events separated by eons can converse through scattered photons. Philosophers have long grappled with the idea of impermanence, but cosmic echoes offer a startling twist. Even the most fleeting phenomena can achieve a kind of immortality. A supernova that flared and vanished before humans walked the Earth still speaks to us through its reflections. its light preserved like a fossil in the interstellar medium. The physicist Alan Lightman poetically noted that we are haunted by the ghosts of stars, pointing to the eerie beauty of this cosmic afterlife. It's a humbling thought our own lives, our civilizations, even our planet are mere flickers compared to these enduring echoes. Yet there's solace in the idea that nothing in the universe truly disappears. It simply transforms, its energy and light repurposed across the ages. The interconnectedness revealed by light echoes challenges the illusion of human separateness from the cosmos. Every atom in our bodies was forged in stellar explosions, and the light we now study is part of the same cosmic dance that brought us into being. The philosopher Thomas Berry captured this beautifully when he wrote, "The universe is a communion of subjects, not a collection of objects." Light echoes embody that communion, linking quasar outbursts to the birth of our solar system, or the death throes of a star to the photons striking a modern telescope's mirror. We're not just observers of this history, we're participants, our very existence shaped by the same forces that send these echoes ricocheting through space. Artists and poets have long drawn inspiration from this interplay of light and time. The painter Vija Selmans recreates star fields with painstaking detail, her canvases echoing the ancient light she studies through telescopes. Composers like John Adams have translated astronomical data into musical scores, where the delays between notes mirror the lag of light echoes across space. Even filmmakers weave these themes into narratives, the haunting final scenes of Tree of Life, with their nebulae and starlight, evoke the same awe that astronomers feel when tracing echoes back to their origins. These creative interpretations remind us that science alone can't capture the full weight of what these echoes mean. They demand a response that's visceral, emotional, as boundless as the cosmos itself. What emerges from this fusion of science, philosophy, and art is a new way of seeing, one where the universe isn't a cold, indifferent void but a vast, resonant chamber. Every echo is a reminder that we're embedded in a story far grander than our own, a narrative written in light and shadow, stretching from the Big Bang to this very moment. And as we learn to listen more closely to these whispers from the past, we're not just uncovering the universe's secrets, we're discovering what it means to be alive within it. Capturing the ethereal beauty of light echoes requires more than telescopes and equations. It demands an artistic eye. Scientists and visual artists have forged an unlikely partnership, transforming raw data into breathtaking depictions that make the invisible visible. Take the iconic visualizations of supernova echoes in planetarium shows, swirling rings of light expanding through interstellar dust, rendered with such precision that viewers feel transported to the cosmic event itself. These aren't mere animations, they're painstaking reconstructions based on spectral data and gravitational models, where every hue corresponds to a specific element and every ripple mirrors actual echo patterns detected by observatories. The Hayden Planetarium's Dark Universe show, for instance, used light echo simulations to illustrate how supernova remnants seed galaxies with heavy elements, a cosmic recycling process made tangible through art. Digital artists like Donna Cox, who leads the Advanced Visualization Lab at the University of Illinois, bridge the gap between science and public imagination. Her team's work on the Cosmic Web project translated terabytes of astrophysical data into flowing, luminous filaments that reveal how light echoes trace the universe's hidden structure. Using volumetric rendering and particle systems, they gave form to theories about dark matter's gravitational influence on echoing photons, concepts that might otherwise remain trapped in academic papers. Similarly, NASA, a conceptual art team, collaborates with astronomers to depict hypothetical echo scenarios, like the planned LISA mission's search for gravitational wave reflections. Their artwork doesn't just illustrate, it inspires, helping secure funding and public support for cutting-edge research. Beyond scientific visualization, light echoes have ignited avant-garde movements. Artist Rafik Anadol's Machine Hallucinations series uses AI to interpret astronomical datasets, generating mesmerizing light projections that evolve like echoes across gallery walls. Composer John Luther Adams translated echo delay times into musical scores, where staggered notes mimic photons bouncing through nebulas. Even traditional media have embraced the theme. Painter Julie Meritou's abstract canvases layer archival telescope images with gestural marks, evoking the palimpsest-like nature of cosmic reflections. These works don't merely depict echoes, they embody their essence, allowing audiences to experience the concept emotionally before understanding it intellectually. The power of these collaborations lies in their reciprocity. Artists push scientists to see their data anew, like when visualizations of the Vela supernova's echo revealed asymmetries that led to revised models of stellar explosions. Conversely, scientific breakthroughs expand artistic vocabularies, as with the James Webb Space Telescope's infrared echoes inspiring neon-infused digital art. Planetariums now routinely host data storytelling nights, where researchers and artists jointly narrate echo discoveries, their complementary perspectives enriching public understanding. Looking ahead, emerging technologies promise even deeper synergy. Virtual reality installations let users stand inside light echo reconstructions, while generative AI helps simulate echo patterns from incomplete datasets. Projects like the Vera-C, Rubin Observatory's public data releases ensure artists will have real-time cosmic events to interpret. As we enter this new era, one truth becomes clear. The marriage of art and science doesn't just communicate discoveries, it fuels them, turning abstract photons into shared human experiences that resonate across cultures and disciplines. The next chapter of light echo research may well be written not just in research papers, but in galleries, concert halls, and immersive experiences that bring the cosmos within reach. The next decade will transform light echo astronomy from a niche field into a cornerstone of cosmic discovery, thanks to instruments so powerful they border on science fiction. The Vera-C, Rubin Observatory, poised to begin its 10-year legacy survey of space and time in 2025, will scan the entire visible sky every 3 nights with a 3.2 gigapixel camera, the largest digital eye ever built. This relentless gaze will catch fleeting light echoes that current telescopes miss, spotting reflections from supernova that exploded before recorded history, or tracking how quasar outbursts ripple through galactic gas clouds over centuries. Imagine a time-lapse movie of the universe, where each frame reveals new echoes flickering to life, tracing the invisible architecture of dark matter filaments or exposing the remnants of long-vanished stars. But raw data alone isn't enough. Here's where machine learning becomes the unsung hero. Traditional analysis might take months to identify a single echo buried in telescope images, but neural networks trained on simulated echoes can scan petabytes of data in hours, flagging anomalies human eyes would overlook. Projects like Google's DeepMind are already collaborating with astronomers to develop algorithms that don't just find echoes but classify them, distinguishing a supernova's reflection from a microlensing event, or even recognizing patterns suggesting entirely new phenomena. One tantalizing possibility: AI might uncover echo storms, cascades of delayed light from ancient cosmic collisions we've never thought to look for. The real game changer could be combining these tools with next-generation space telescopes. NASA's Nancy Grace Roman Space Telescope, launching around 2027, will carry a coronagraph capable of blocking starlight to reveal exoplanet echoes in unprecedented detail. Meanwhile, the European Extremely Large Telescope's 39-meter mirror, nearly half the length of a soccer field, will dissect echospectra with enough precision to detect molecular oxygen or methane in reflected exoplanet atmospheres, potential signatures of life. Together, these instruments could turn light echoes into a universal translator for cosmic history, decoding everything from the formation of the first black holes to the chemistry of alien worlds. Yet the greatest discoveries often lie in the gaps, the questions we haven't even learned to ask yet. Why do some supernova echoes show bizarre spectral lines that defy nuclear physics models? Could certain repeating echo patterns be evidence of primordial black holes or other exotic objects? And what about the controversial claims of too early galaxy echoes spotted by James Webb, which some theorists argue might force a rewrite of cosmic dawn timelines? Each mystery is a thread waiting to be pulled, potentially unraveling our understanding of dark energy, quantum gravity, or the universe's ultimate fate. Challenges loom as large as the opportunities. Radio frequency interference from satellite mega-constellations like Starlink threatens to drown out faint echo signals, especially at the critical hydrogen wavelength used to study the early universe. Funding battles rage over whether to prioritize giant observatories or distributed networks of smaller telescopes better suited for echo monitoring. And there's the sheer computational cost. Processing light echo data from the Rubin Observatory could require exascale supercomputers that don't yet exist. But if history teaches us anything, it's that where light travels, curiosity follows. These obstacles aren't dead ends, they're signposts pointing toward innovations we haven't yet imagined. What's certain is that light echoes are no longer just cosmic curiosities, they're becoming one of astronomy's most versatile tools. As technology peels back layer after layer of these time-delayed signals, we're not just observing the universe's past, we're learning to navigate its future. The echoes that reach telescopes tomorrow may carry answers to questions that haven't yet occurred to us, whispered across the ages by light itself. Studying light echoes is like trying to hear a whisper in a hurricane. The universe bombards us with light from countless sources, and teasing out these faint, delayed signals demands near impossible precision. One of the biggest hurdles, the sheer overwhelming glow of everything else. Modern telescopes must contend with light pollution from cities, the glare of nearby stars, even the infrared warmth of Earth's own atmosphere, all of which can drown out the subtle flicker of an echo. It's not just about brightness either. Cosmic dust clouds, the very surfaces that create echoes, also absorb and scatter light, distorting the signals astronomers are desperate to capture. A reflection that left its source with crisp details might arrive at our telescopes stretched, dimmed, or fragmented, like a message passed through a game of celestial telephone. Then there's the time problem. Unlike a supernova's initial flash, which commands attention for weeks, light echoes unfold over years, decades, even centuries. Monitoring them requires patience and persistence, resources often at odds with the short funding cycles of scientific research. Consider the case of Supernova 1987A. Astronomers have tracked its echoes for over 3 decades, and only now are they piecing together the full 3-dimensional structure of the debris field around the explosion. Many echoes slip through the cracks simply because no telescope happened to be pointed in the right direction at the right moment. It's a cosmic version of missing a once-in-a-lifetime photo because your camera was turned off. The faintness of these signals pushes technology to its limits. Even the most advanced detectors, cooled to near absolute zero to minimize noise, struggle to distinguish echoes from random fluctuations. Radio telescopes hunting for the faint whispers of hydrogen from the cosmic dawn must contend with interference from cell phones, satellites, and even the Milky Way's own radio hum. Space-based observatories like James Webb avoid some of this noise, but they come with their own challenges: limited lifespans, unforgiving orbits, and the cruel reality that a single malfunction can end a billion-dollar mission prematurely. Perhaps the most underappreciated challenge lies in interpretation. Light echoes don't arrive with labels explaining their origins. A faint ring of light could be the reflection of a supernova, a quasar's outburst, or something entirely unknown. Disentangling these possibilities requires cross-disciplinary collaboration: astrophysicists working alongside chemists to decode spectral lines, computer scientists developing algorithms to model echo paths, even mathematicians refining the geometry of how light bends around cosmic structures. Missteps can lead to false breakthroughs, like the controversial claim in 2018 that echoes from a distant galaxy revealed evidence of cosmic strings, later shown to be an artifact of data processing. Despite these obstacles, global efforts are turning the tide. Projects like the Square Kilometre Array, a sprawling network of radio telescopes across 2 continents, will scan the sky with unprecedented sensitivity, while space missions like the European Space Agency's Ariel probe will analyze exoplanet atmospheres by studying their starlight echoes. Citizen science initiatives, where volunteers comb through telescope data, have already uncovered previously missed echoes hiding in plain sight. The challenges remain daunting, but the rewards decoding the universe's oldest messages are too profound to ignore. Every technical hurdle overcome isn't just progress, it's another step toward hearing the cosmos speak on its own terms. Light echoes don't recognize borders, they ripple across the cosmos, indifferent to the divisions that fragment humanity. This universality has forged an unprecedented era of global collaboration in astronomy, where researchers from rival nations unite under the banner of shared curiosity. Take the Event Horizon Telescope, a planet-sized observatory linking dishes from Antarctica to Spain, from Hawaii to the South Pole. While famous for capturing the first image of a black hole, its network also studies light echoes from active galaxies, combining data so precise it can track photons bouncing off dust clouds thousands of light years away. Each participating telescope contributes a unique piece of the puzzle. High-frequency observations from Chile's ALMA array reveal chemical fingerprints in echoes, while Greenland's icy isolation provides noise-free radio data. It's a symphony of technology and geography, proving that decoding the universe requires more than one nation's resources. It demands a chorus of perspectives. The secret to these collaborations lies in open science. When Japanese astronomers detected an unusual echo pattern from a supernova in 2021, they didn't hoard the data, they shared it within hours via the Transient name server, a global alert system. Within days, American spectrographs confirmed heavy elements in the reflection. European radio telescopes mapped the expanding debris field, and Australian theorists modeled the explosion's asymmetry. This rapid-fire teamwork turned a fleeting observation into a landmark study on how dying stars seed galaxies with life's building blocks. Even politically tense regions find common ground. Israeli and Iranian researchers co-authored a paper on quasar echoes, their analysis of shared data revealing previously unknown gas filaments between galaxies. Amateurs aren't left out of this collective effort. Platforms like Zooniverse's Supernova Echo Hunt train volunteers to spot delayed reflections in telescope images, leading to discoveries professionals might miss. In 2023, a German schoolteacher sifting through data from the Pan-STARRS survey flagged an odd ring of light later confirmed as the first echo from a rare, failed supernova, where a star collapsed directly into a black hole. Even backyard astronomers contribute, with high-quality DSLR cameras capturing echoes from nearby stellar explosions like Velas, their observations filling gaps between professional scans. The future of echo research hinges on this democratization. Projects like the upcoming Rubin Observatory will release real-time alerts, enabling amateurs with modest telescopes to track emerging echoes. Citizen scientists in Kenya are already testing low-cost radio antennas to monitor hydrogen echoes from the cosmic dawn, while a crowdsourced network in Chile photographs the Milky Way's dust clouds nightly, creating a living map of reflection surfaces. These efforts prove that unraveling cosmic mysteries isn't reserved for elites with billion-dollar tools. It's a human endeavor, where every pair of eyes, whether trained on a laptop or a mountaintop observatory, expands our vision of the universe. What emerges from these partnerships is more than scientific progress. It's a blueprint for cooperation. In tracing light that predates civilizations, we're reminded that curiosity transcends politics, that the cosmos speaks a language all can understand. The same echoes that reveal stellar deaths also whisper something profound. When humanity unites under the night sky, there's no limit to what we can discover. The universe doesn't reserve its secrets for professional astronomers. Some of the most groundbreaking discoveries about light echoes have come from everyday stargazers, teachers, and even teenagers armed with nothing more than curiosity and an internet connection. Citizen science has become the unsung hero of echo research, turning the hunt for these cosmic whispers into a global team effort where anyone can contribute. Platforms like Zooniverse's Supernova Hunters train volunteers to scan telescope images for the faint rings and arcs that betray an echo's presence. It's a cosmic version of Where's Waldo, except instead of a striped shirt, you're searching for the ghostly glow of a star that died centuries ago. One of the most inspiring success stories comes from a retired schoolteacher in Australia. While sifting through data from the Pan-STARRS telescope in 2021, she spotted an unusual smudge near the galaxy NGC 4992. At first glance, it looked like a camera artifact, but her persistence paid off. The smudge turned out to be a light echo from a supernova that exploded over 400 years ago, its reflection only now reaching Earth. Professional astronomers had missed it because the echo was offset from the galaxy's center, where supernovae are typically expected. Her discovery led to a re-examination of archival data, revealing 5 more echoes from the same event, painting a 3-dimensional map of the interstellar dust clouds it illuminated. Then there's the story of a high school student in Norway who joined the Disk Detective Project, a NASA-led initiative to study debris disks around stars. While most participants focused on identifying planet-forming disks, this student noticed something odder, a star with strange, asymmetrical brightening that didn't match any known disk behavior. After flagging it, astronomers realized he'd found a rare mirror nebula, where light from a recent stellar outburst was echoing off a nearby dust cloud. His sharp eyes added a new entry to the catalog of known light echoes and earned him a co-author credit on a peer-reviewed paper. The beauty of these projects lies in their accessibility. You don't need a PhD or a backyard observatory, just a computer and a willingness to learn. Platforms like Backyard Worlds, Planet 9 guide users through real astronomical data with interactive tutorials, teaching them to distinguish echoes from camera noise or distant galaxies. Some volunteers specialize in color analysis, using tools to measure how an echo's hue shifts over time, a clue to the chemical composition of the reflecting dust. Others track echo expansion rates, helping calculate distances to unseen interstellar clouds. It's a collaborative puzzle where every participant, regardless of background, can piece together part of the cosmic picture. Beyond discoveries, these initiatives have an educational superpower. They demystify the scientific process. Participants don't just click buttons, they engage in forums where professional astronomers explain their findings, join live Q and as about ongoing research, and even suggest improvements to classification tools. A teacher in Brazil used the Galaxies Echo project to design a classroom unit on the speed of light, letting students measure delays between supernova and their echoes to calculate cosmic distances firsthand. In rural India, a community astronomy group used echo data to create art installations that visualized deep time, bridging science and local storytelling traditions. This isn't just about astronomy, it's about redefining who gets to explore the universe. When a nurse in Kenya or a fisherman in Alaska can contribute to cutting-edge research, it reshapes our cultural relationship with science. Light echoes, once the domain of elite observatories, have become a shared human heritage, their study a testament to what we can achieve when knowledge is open and inclusive. And as these collaborations grow, they're not just answering old questions, they're uncovering mysteries we didn't even know to ask. Who knows what hidden echo, what overlooked reflection, might be waiting for the right pair of eyes to find it? The next great cosmic revelation could come from someone watching this video, maybe even you. Light echoes aren't just tools for astronomers, they're gateways to wonder, transforming classrooms and planetariums into launch pads for the next generation of cosmic explorers. Picture a high school physics class where students don't just memorize equations, but use real data from the Chandra X-ray Observatory to track the expansion of a supernova's light echo across months of images. By measuring the ring's growth and applying the speed of light, they calculate the distance to the dust cloud it's illuminating, a hands-on lesson blending geometry, physics, and cosmic history. Programs like NAS, a universe of learning, provide educators with these ready-made activities, turning abstract concepts into tangible discoveries that spark curiosity far beyond textbook diagrams. Planetariums have embraced light echoes as storytelling gold. The California Academy of Sciences' Invisible Worlds show uses immersive projections to let audiences walk through a three-dimensional reconstruction of supernova echoes, revealing how these reflections map otherwise invisible dust structures. Meanwhile, the Adler Planetarium in Chicago hosts Echo Hunt workshops, where families analyze telescope images to spot delayed light from stellar explosions, earning digital badges for verified discoveries. These experiences demystify the scientific process, showing that cosmic exploration isn't reserved for experts with advanced degrees. It's an adventure open to anyone willing to look up and ask questions. For those craving deeper dives, citizen science platforms like Zooniverse offer front-row seats to cutting-edge research. The Supernova Safari project guides volunteers through classifying potential light echoes in data from the Vera Sea. Rubin Observatory's precursor surveys, participants don't just click buttons, they join live Q and, as with astronomers, learning how their classifications contribute to papers published in peer-reviewed journals. It's science without barriers, where a retired teacher in Portugal or a teenager in Indonesia can make genuine contributions to astrophysics. Behind these educational initiatives are researchers whose own journeys began with moments of cosmic awe. Dr. Tamara Davis, an astrophysicist mapping dark matter with light echoes, recalls how a childhood visit to a rural observatory where she saw photographs of supernova remnants ignited her passion. The idea that light could carry stories across millennia, she says, made me realize the universe was a puzzle waiting to be read. Similarly, Dr. Brian Schmidt, a Nobel laureate who used supernova echoes to prove cosmic acceleration, credits a high school astronomy club's telescope sessions for his career path. These personal stories underscore a powerful truth. Every groundbreaking discovery begins with someone, often a young student, being captivated by the cosmos whispers. Resources for aspiring echo hunters abound. Free online courses like Quasars, Astrophysics, Exploring Exoplanets, include modules on light echo analysis, while libraries loan out echo kits with DIY spectroscopes to dissect starlight. Podcasts like Astronomy Cast break down complex echo physics into bite-sized episodes, and YouTube channels like PBS Space Time visualize these phenomena with stunning animations. The message is clear: you don't need a billion-dollar telescope to explore the universe's echoes, just curiosity, a bit of guidance, and the willingness to listen closely to light's ancient stories. What unites these educational efforts is their power to bridge time and space, connecting learners not just to cutting-edge science but to the human stories behind it. When a student measures the delay of a supernova's echo, they're not just solving a math problem, they're touching a piece of cosmic history, joining a lineage of thinkers who have turned fleeting glimmers into profound truths. And somewhere in that process, between the data points and the aha moments, the next great cosmic detective might just find their calling. Dr. Priya Patel still remembers the night she almost missed her greatest discovery. Camped at Chile's Los Campanas Observatory in 2018, she'd spent weeks tracking what seemed like a routine supernova echo in the spiral arms of NGC 1365. "I was exhausted," she admits, ready to pack up when my software flagged a faint secondary ring no one had predicted. That ghostly circle turned out to be light from the same explosion, but bounced off a previously unknown dust cloud 40 light-years behind the galaxy. Suddenly, we weren't just studying one echo, we had stereo vision. Her team's subsequent three-dimensional reconstruction revealed the supernova had erupted inside a vast stellar nursery, its shockwaves triggering new star formation, a cosmic domino effect captured through delayed photons. For Dr. Carlos Mendes, light echoes aren't just data points, they're time machines. Growing up in Puerto Rico with limited telescope access, he now leads a project using echoes to probe the Milky Way's dark age before the first stars formed. "We're essentially repurposing dust clouds as cosmic recording devices," he explains. His breakthrough came when cross-referencing radio echoes with gravitational wave detections, catching the aftermath of two neutron stars colliding, an event whose visible light had faded centuries earlier. The echo arrived like a postcard from the past, stamped with details about heavy elements we'd never have seen otherwise. Not all revelations come from high-tech observatories. Dr. Amina Yusuf's team in Nigeria made headlines by modifying old satellite dishes to detect hydrogen echoes from the universe's first billion years. "Everyone said we needed million-dollar equipment," she laughs. But sometimes ingenuity outsmarts budgets. Their frugal approach uncovered an anomaly, echoes suggesting early galaxies formed stars in sudden bursts rather than steadily, challenging prevailing models. Meanwhile, in Australia, Indigenous astronomer Carly Noon blends traditional sky knowledge with modern astrophysics. "My ancestors tracked celestial events through oral records spanning generations," she notes. Light echoes are science's version of those stories, messages from ancestors written in photons. The human side of this research shines through in moments of vulnerability. Dr. Henry Lin recounts spending 3 years chasing what turned out to be a camera artifact masquerading as an echo. "Failure teaches you humility," he reflects. "The universe doesn't care how badly you want a discovery. Conversely, Postdoc Maria Kowalski describes the eerie beauty of watching a supernova echo brighten exactly as her models predicted on the anniversary of her mentor's passing. It felt like the cosmos was winking at us. These personal journeys ripple beyond academia. When Dr. Patel's discovery inspired a Bollywood film's climax, where characters decipher echoes to save Earth, she realized science's cultural power. Suddenly, taxi drivers in Mumbai were asking me about time-delayed light. Similarly, Dr. Mendes's work features in Puerto Rican poetry, symbolizing how island communities maintain connections across diaspora. Perhaps most moving is the Echo Project, where school children worldwide adopt a light echo, tracking its evolution while learning about perseverance, both photons and their own. What unites these researchers isn't just technical skill, but a shared sense of stewardship. As Dr. Noon puts it, we're not just decoding echoes, we're ensuring these cosmic stories get passed on, whether through peer-reviewed papers or bedtime stories under the stars. Their work reminds us that behind every dataset are people who have devoted lifetimes to listening for whispers from the dark. Light echoes have transcended the realm of astrophysics to become a powerful metaphor in storytelling, their ethereal beauty inspiring creators across every medium. Science fiction films like Interstellar and Arrival weave echo-like phenomena into their narratives, using delayed signals as plot devices that blur time and space. In Interstellar, the protagonist communicates across dimensions by manipulating gravitational waves, a concept echoing real-world light reflections, while Arrival's linguist deciphers alien language through circular symbols that ripple like photons bouncing off cosmic dust. These stories tap into the universal fascination with messages from the past, mirroring humanity's own quest to decode the universe's ancient whispers. Literature, too, has embraced the poetry of cosmic reflections. Kim Stanley Robinson's Aurora imagines a generation ship where colonists analyze light echoes to reconstruct Earth's lost history, while Ted Chiang's story of Your Life, The Basis for Arrival, explores how perception of time shifts when viewing events through delayed light. Even fantasy isn't immune. N.K. Jemison's The Broken Earth trilogy uses geological echoes as a metaphor for trauma reverberating through generations, drawing direct parallels to astrophysical phenomena. What unites these works is their treatment of light echoes as bridges between eras, allowing characters and readers to confront the impermanence of existence while finding solace in continuity. Musicians have translated these concepts into soundscapes. The ambient composer Brian Eno's Reflection album layers looping synthesizer tones to mimic the way light echoes overlap in space, creating aural patterns that shift like celestial reflections. Rock bands like Muse weave echo imagery into lyrics about cosmic isolation, while hip-hop artist Open Mike Eagle's Light Echoes uses the phenomenon as a metaphor for cultural memory. These artistic interpretations reveal a shared human response. Light echoes symbolize our longing to leave marks that outlast us, whether through art, discovery, or the simple act of looking up. Why does this concept resonate so deeply? Psychologists suggest it taps into primal instincts, the same awe our ancestors felt when hearing their voices bounce off canyon walls, now scaled to cosmic proportions. There's also an ethical dimension to this fascination. As we project stories onto light echoes, we're forced to confront our responsibility as temporary custodians of knowledge. If civilizations billions of years from now uncover our own echoes, radio transmissions, space probes, or even altered atmospheric chemistry, what legacy will they decipher? This duality, the interplay of scientific wonder and moral introspection, makes light echoes uniquely compelling. They're not just astronomical tools, they're mirrors reflecting our best and worst impulses back at us. This cultural journey inevitably circles back to a pressing question. As we grow adept at capturing cosmic whispers, how do we ensure this knowledge benefits all of humanity? The same telescopes that trace ancient photons often sit on lands contested by indigenous communities, while the data they produce remains inaccessible to many. Perhaps the next chapter of light echo research shouldn't just focus on technical breakthroughs, but on who gets to participate in and profit from their discovery. After all, the universe's echoes belong to no one, yet they speak to everyone. Exploring the cosmos comes with profound ethical responsibilities, not just for scientists, but for all of humanity. Every time we train a telescope on distant galaxies or decode ancient light echoes, we're not just observers, we're custodians of a shared cosmic heritage. Think of it like unearthing an archaeological site, except instead of delicate pottery, we're handling photons that have traveled billions of years to reach us. The stakes are high. Mishandle this legacy, and we risk losing irreplaceable insights into the universe's origins. But hesitate to explore, and we deny future generations the chance to learn from the stars. Striking that balance requires more than technical skill. It demands humility, foresight, and a commitment to preserving the cosmos, not just for study, but for wonder. One of the most pressing ethical challenges is light pollution, a problem that grows worse with every unchecked city light or sprawling satellite constellation. For centuries, humans gazed up at a pristine night sky, but today, artificial glow drowns out all but the brightest stars for a third of the world's population. The consequences ripple far beyond romantic stargazing. Observatories struggle to detect faint cosmic signals, from distant supernova to the subtle whispers of light echoes. Projects like the Vera C. Rubin Observatory, designed to map the universe in unprecedented detail, now race against the clock as mega-constellations like SpaceX's Starlink streak across their fields of view. It's a classic tragedy of the common's individual conveniences collectively dimming humanity's window to the cosmos. Yet the ethics of cosmic exploration extend beyond what we obscure. They also encompass what we preserve. Some scientists argue for treating certain regions of space as cosmic heritage sites. Imagine designating the vicinity of a historic supernova, like Kepler's star of 1604, as protected interstellar space, where future probes or mining operations would tread lightly to avoid disturbing its light echoes. Others advocate for quiet zones in the radio spectrum, shielding frequencies used by natural cosmic phenomena, like the 21-centimeter line emitted by hydrogen, our primary tool for mapping the early universe from human-made interference. These aren't abstract ideals, they're practical safeguards ensuring that the cosmos remains legible for generations to come. Inclusivity is another critical frontier. For too long, access to space research has been gatekept by wealth and geography. The world's most powerful telescopes cluster in a handful of privileged locations, while communities near the equator or in the global south often lack even basic observational tools. Initiatives like the African VBI network are challenging this imbalance, building radio telescope arrays across the continent and training local researchers to lead groundbreaking studies. Meanwhile, open data policies from NASA and ESA allow amateur astronomers in Mumbai or Nairobi to analyze the same cosmic datasets as Ivy League professors. True ethical exploration means democratizing discovery, ensuring the universe's stories aren't monopolized by a select few, but shared as a common human inheritance. The choices we make today will echo across centuries. Will we prioritize short-term gains like unfettered satellite expansion or resource extraction on the moon over the long-term health of our cosmic perspective? Or will we adopt principles akin to the leave no trace ethos of environmentalism, committing to explore space sustainably? The answers hinge on recognizing that the universe isn't just a resource to exploit or a puzzle to solve. It's a shared museum, a library, and a classroom rolled into one. Every photon we capture, every echo we decode, is part of a grand narrative that transcends borders and generations. As we stand on the threshold of deeper exploration, from crude Mars missions to next-generation telescopes, we're not just shaping the future of science. We're deciding what kind of ancestors we'll be for those who will one day look back at our era, searching for their own light echoes in the artifacts we leave behind. Will they find a legacy of heedless expansion or one of thoughtful stewardship? The universe has given us 13.8 billion years of history to study. The least we can do is ensure its next chapters are worthy of that inheritance. Humanity stands on the brink of a new era, one where light echoes could become our roadmap to the stars. Picture spacecraft equipped with solar sails, riding beams of reflected starlight to distant nebulas where cosmic whispers linger. These wouldn't be passive voyages, they'd be precision chases, navigating by the delay between an echo's arrival and its original burst, using the universe's own reflections as guideposts. Imagine a probe parked near the Vela supernova remnant, its instruments trained not on the fading explosion, but on the ripples still expanding through nearby dust clouds, a real-time laboratory for studying stellar death and rebirth. The data from such missions could rewrite physics textbooks. Echoes from gamma-ray bursts might carry subtle distortions, hints of quantum gravity or extra dimensions warping spacetime in ways invisible to Earth-bound detectors. Ancient quasar reflections, analyzed up close, could reveal if the fundamental constants of nature have shifted over billions of years. Even darker mysteries await. Some theorists speculate that certain echo patterns, unnaturally sharp or geometrically precise, might betray the presence of alien megastructures, vast mirrors or lenses intentionally placed to communicate across millennia. While far-fetched, the possibility reminds us that light echoes aren't just relics. They're potential message bottles floating on the cosmic tide. Beyond hard science, these reflections invite philosophical revolutions. If future telescopes detect echoes of civilizations long extinct, perhaps the afterglow of their energy use or the spectral fingerprints of industrial atmospheres, we'd confront a profound truth. Intelligence might be common in the universe, but fleeting. Conversely, finding no such signals would be equally startling, suggesting we're either improbably early or tragically alone. Either way, light echoes force us to reckon with humanity's temporal footprint. The civilizations we admire in history books lasted centuries. The stars we study span billions of years. Our own legacy, like those before us, may ultimately be measured in photons scattered toward unknown futures. This journey through cosmic echoes has taken us from the universe's fiery birth to its whispered secrets. We've seen how primordial light sculpted galaxies, how dying stars etch their stories in interstellar dust, and how every reflection is a palimpsest layers of history waiting to be decoded. But the most thrilling chapter may be unwritten. With each technological leap, from James Webb's infrared eyes to the quantum sensors of tomorrow, we gain new ways to listen. The universe isn't silent, it's a cathedral of echoes, and we're only beginning to learn its language. So the next time you gaze at the night sky, remember, you're not just seeing stars. You're witnessing an epic still unfolding, one reflected photon at a time. From the first flicker of starlight piercing the cosmic dark to the intricate webs of reflection mapping our universe today, light echoes have served as both historians and prophets of the cosmos. They carry tales of stellar explosions that shaped our galaxy, whispers from quasars that illuminated the early universe, and even clues about planets that might harbor life. These scattered photons are more than remnants, they're active participants in an ongoing dialogue between past and present, inviting us to decode messages older than Earth itself. Consider the sheer scale of this conversation. When you gaze at the Orion Nebula, you're not just seeing a stellar nursery, you're catching reflections of light that left those stars decades ago, bouncing off dust clouds before finally reaching your eyes. The Hubble Space Telescope's iconic image of the light echo around V838 Monocerotis isn't just a pretty picture. It's a time-lapse of light itself, revealing layers of interstellar terrain like a celestial ultrasound. Every echo is a palimpsest with newer reflections overwriting older ones, creating a living archive of cosmic events. What makes this so extraordinary is how accessible the wonder remains. You don't need a PhD or a space telescope to participate. Step outside on a clear night, and the starlight hitting your retina includes photons that have traveled for years, centuries, even millennia. Some may have ricocheted off asteroids or passed through the atmospheres of alien worlds before reaching you. That faint glow of the Milky Way, it's a mosaic of light echoes with contributions from stars that died before human civilization began. The implications stretch far beyond astronomy. Light echoes challenge our perception of time as linear and absolute. They prove the past isn't locked away, it's still out there, racing through space, waiting to be captured by anyone curious enough to look. Researchers using echoes to study dark matter are essentially performing cosmic archaeology, while artists transforming echo data into soundscapes remind us that science and creativity spring from the same sense of wonder. This is why we explore, not just to catalog stellar phenomena, but to find our place in a story that began with the Big Bang and will continue long after our sun burns out. Every echo decoded is another stitch in the tapestry of understanding, connecting quasar outbursts to the iron in our blood, supernova shockwaves to the atoms in our devices. The universe isn't a static backdrop, it's a dynamic, interactive stage, and we're finally learning its cues. So tonight, when you step outside, take a moment to really see the sky. That flicker of a satellite, it's humanity's own tiny echo in the cosmos. The steady glow of Mars, a reflection of sunlight that left its surface minutes ago. You're not just an observer, you're part of the exchange, catching whispers from across time and space. And who knows, maybe someday, our own signals, radio waves, laser pulses, even the chemical traces of our civilization, will become echoes for someone else to find. Until then, keep looking up, keep questioning, and remember, the universe is still speaking. All we have to do is listen.